In this section, we're going to be talking about kinetics. We'll relate those to rate laws, Arrhenius equation, and reaction coordinate diagrams. In this section, we're going to be talking about the kinetics, the rate of the chemical reaction. How fast a chemical reaction goes is just as important as whether it's energetically favorable or not. We can actually look at the kinetics by measuring how fast the concentration of reactants disappears or how fast the concentration of our products appears. There are certain variables that we need to determine that will affect the rate of the chemical reaction. First of all, our molecules have to actually bump into each other. So that's the number of collisions per unit time. They also have to have enough energy to react, and they have to be oriented in the right direction. In other words, the functional group of the molecule has to actually interact with the functional group of another molecule. For example, the nucleophile and the electrophile. The rate equation is also called the rate law, and it's given here. It's equal to, the rate is equal to a rate constant times the concentration of A raised to some power times the concentration B raised to some power. And this B and A, the little a and B, are called the order of the reaction. That means, is my rate dependent on the concentration of A or not? Is my rate dependent on the concentration of B or not? Or do I need two B molecules to be involved? And so that order and the rates themselves all have to be experimentally determined. You can't do it from first principles. So the order of the reaction is the number of molecules in the rate determining step, the number of collisions per unit time essentially. So we have to keep that in mind. So for example, if I look at this chemical reaction where I have bromomethane reacting with a hydroxide anion under the reaction conditions of acetone and water, I get methanol and bromide anion. When I determine the rate, I change the concentration of one and then I measure whether that makes it go faster or slower. And when I come up with, when I'm all said and done, measuring the rate and measuring changing concentrations of my reactants, it turns out the rate of this reaction is dependent on both the concentration of my bromomethane and my hydroxide. So both of them have to be present, and you can see there are no orders here, so they're all order 1. I need concentration 1 for each of those. If I look at a rate constant for this reaction where I have this tertiary alkyl halide reacting with hydroxide and acetone and water, I get my products. If I go and I measure the rate and I change the concentration of my tertiary alkyl halide and I change the concentration of my hydroxide, it turns out when I measure the rate, it doesn't matter what the concentration of hydroxide is. It only matters what the concentrate of my tertiary alkyl halide is. So my rate law becomes rate constant times the concentration of my tertiary alkyl halide. What that's telling us about these reactions that they have different mechanisms. I'd have to draw my reaction arrows differently, and more experiments are required to actually determine what that mechanism is. So it's important to determine the rate laws for chemical equations because it predicts and informs us a little bit about the reaction mechanism. Okay. Again, rate laws must be determined experimentally. I can't predict them. Okay. So how does that relate to the Arrhenius equation? So in this case, I have the rate law is equal to A times e to the e sub a over r sub t, where A is actually a frequency factor. That frequency factor tells us how frequently we collide with molecules. So it has to do with this portion of our rate of reaction. Okay, this e sub a, it actually tells us how much energy is required, and then R and T are just the gas constant and temperature in degrees Kelvin. And so the E sub A is acting an energy barrier. And let's look at that. So if I look at this chemical reaction where I have methane reacting with a chlorine radical. It goes through a transition state, which can be observed experimentally to form a radical, carbon radical, and HCl gas. I have my reactants, I have my products. Notice that my barrier here from going from reactants to products is considered my activation energy. That's how much energy is required, because in order to get to my products, I have to go over that. This double bar here is actually the transition state. This is considered a concerted reaction, meaning that I'm making bonds and breaking bonds at the same time. So I also need to have the proper orientation at my transition state in order for this chemical reaction to occur. How about activation energy as a function of temperature? I know that some chemical reactions go faster at higher temperatures. Again, I look at my Arrhenius equation and I see a temperature variable in here. So at higher temperatures, my rate should increase, looking at the math. And we can sort of justify that looking at the population of molecules that have that activation energy. So activation energy stays the same. So let's look at room temperature here. That's that black line here. Here is my energy profile. This is pointing energy in the x direction. And this is the fraction of molecules that have enough energy. So right here at this point, I can see it's room temperature. And over here, what if my activation energy was 4 kilojoules per mole? This blue region here is only the number of molecules that have that energy. None of these will react, okay, because they don't have enough energy. If I raise the temperature, my profile changes. So I've changed my amount of energy in the reaction vessel. And now you can see if I have a 4 kilojoule per mole activation energy, I have all of these molecules now have enough energy. In this whole, all these colored regions have enough energy to react, and so it reacts faster. I have sufficient energy for a lot of molecules to react, and then they react. So let's look at a multi-step reaction where I actually have reaction intermediates. So in this reaction, I'm starting with methane in a chlorine radical. I have an activation energy of 17 kilojoules per mole to get up to my rate limiting transition step, and then I form a product. This product actually isn't the final product, so this would be an endothermic step in my reaction. There's another step where I need some more energy to go over another activation energy barrier and down to finally to my products. Okay, so the highest activation energy, one I have is 4 kilojoules per mole, and the other one I have 17. It's considered my rate limiting step. It's the slowest step because it takes the most energy. So transition states are energy maximums. I have one transition state here and one transition state here. And intermediates are usually energy minimums. So here's an energy minimum between my reactants and final products here. That's the entire reaction coordinate for this chemical reaction. Okay. This is not the rate limiting step again because it's only have a 4 kilojoules per mole energy, and this would be my reaction intermediate energy level. Now the difference between my starting materials and my products from an energy standpoint, my enthalpy is minus 105 degrees, even though I had to put in 17 kilojoules per mole to get the reaction started. Now let's look at the following reaction step, going from my reaction intermediate to my reaction product. I have an activation energy of 4 kilojoules per mole. I have an enthalpy change of 109, so I'm going from this energy level down to this energy level, so thermodynamically it's very favorable. Let's actually give the equation for the reverse reaction. Since this is an equilibrium, I can actually go backwards on this reaction coordinate. And what would that reaction look like? That would be my chloromethane plus my chlorine radical, giving my methyl radical and my chlorine molecule. Let's calculate the activation energy and the delta H for this reverse reaction. Well, in this case, I have to go from this level up to this highest energy here is my activation energy. So that's going to be 109 plus my 4, and that's going to be 113. The energy difference is still going to be 109, but it's going to be in the positive direction, meaning it's an endothermic reaction to go in the reverse direction. What does this tell you about the reverse process? That it's not likely to occur because I have a very high activation energy. If I were to get the molecules to go back this way, they would just fall back down to the thermodynamically more stable point because there's plenty of energy in the system. So what does that activation energy mean in a practical sense? So if I look at activation energies, and I have 4 of them here related to this chemical reaction where I have a halide radical reacting with methane to form my acid and my methyl radical. If I have an activation energy of 5 kilojoules per mole, I literally have a rate of 140,000 per second reactions that will occur. If I raise the temperature, I have 300,000 reactions that will occur if I have enough material per second. In fact, fluorine is actually very explosive because it reacts so fast. If I now look at chlorine reaction with methane, I have an activation energy of about 17 kilojoules per mole. There I have a very controlled reaction. I have about 13,000 reactants per second going on. If I want it to go faster, I can raise the temperature and still have a good reaction rate and still make product, but not explosive. If I use bromine, my rate is minuscule. In fact, I have to raise the temperature just to get any product whatsoever because the activation barrier is so high with bromine. If I look at iodine, no matter what I do, I get very little product. Even with heating, it doesn't help. So those are the practical aspects of activation energy relative to rates of chemical reaction and temperature. Let's look at some reaction coordinates, and there's a variety of them that occur, and they're all different. Let's actually identify and classify the following items in these 4 reaction coordinates. The reactants of products, whether the reaction is exothermic or endothermic, whether it's a single step or multi-step reaction, what is the rate limiting step, what are the intermediates, and where are the transition states. Let's start out here on the first one. We usually always consider the minimum to the left to be my reactants and the minimum to my far right to be my products, and that'll be true on all of these. So what is this? Is this exothermic or endothermic? Well, this would be endothermic because my products are at higher energy than my reactants. This is not a thermodynamically favorable reaction. Is this a multi-step or single step? It's multi-step, right? I got an intermediate. So let's look at the rate limiting step here. That would be this first step. That is the highest activation energy that I need to get up here. Once I'm up here, I have enough energy to get down to my products here. So I have intermediates. That is my reaction minimum between my reactants and products. And I have 2 transition states. If I look at my second one here, let's just list our reactants and products. Is this going to be exothermic or endothermic? This is actually going to give off energy because my products are more stable. So I lose energy and I release that in the form of heat typically. This is also going to be a multi-step process because I have a reaction intermediate. My rate limiting step looks like my first one here because from here to here is higher than from here to here. In this case, I'm going to have 1 intermediate and 2 transition states again. If I look at my third reaction coordinate, put in my reactants and products. Is this going to be a single step or multi-step? It's just a single step. There are no reaction intermediates. So this is also going to be endothermic because my products are more stable than my reactants. So it's thermodynamically more favorable. It's a single step process. And I have 1 transition state here, an energy maximum. And what is my rate limiting step? That's the only step. If I look at this reaction coordinate, I have my reaction and products. This is also going to be exothermic because my products are lower in energy than my reactants. It's going to be multi-step because it has a reaction intermediate, which is going to be my rate limiting. That's going to be my second step this time. I can put this much energy in and get this far along my reaction coordinate, but I need more energy to get to my final products. So I have my reaction intermediate, and I have my two transition states. Now let's look at a very specific reaction. Let's look at alkene hydrogenation and use it as a model for doing chemical reaction. And we can actually relate this back to the stability of alkenes by doing hydrogenation reaction. So here's an example of a hydrogenation reaction. I take an alkene, I react it with hydrogen in the presence of a palladium and carbon catalyst, and I get an alkane. So I'm going from an unsaturated alkene to a saturated alkane. And this is just another example. I start off with an alkene. I had hydrogen across this double bond, one hydrogen to this carbon, one hydrogen to this carbon. I form the alkane. The number of carbon-hydrogen bonds increases. How does that chemical reaction look in sort of a pictorial standpoint? These green balls all represent my catalyst. I have hydrogen gas that is absorbed onto the surface of the catalyst. My pi electrons are actually attracted to that same catalyst, so they get attracted toward that palladium carbon catalyst, and when they do, they get close to those hydrogens, and these electrons then on my pi bonds, they tend to pick up those hydrogens that are absorbed onto the surface of my catalyst. So I go from an alkene and hydrogen, I approach my catalyst, I start making and breaking bonds, and I form the alkane, a catalytic chemical reaction. So if I look at that chemical reaction, I can actually measure the energy that is released during that chemical reaction. And if I look at this energy released, depending on how I'm substituted, I get different energies released. Okay? So in one case, if I look at my substitution pattern where I have my alkene here has 1, 2, 3 alkyl groups attached to my double bond carbons. Here I only have 1, 2 carbons attached to my carbon double bonds, and here I only have 1 carbon. So this is more substituted as I move up, and if you look at that, you can see that I have more energy released the least substituted I have. That implies that my more substituted reactants were actually more stable doing this chemical reaction because my products are the same. One way to look at that is using a reaction coordinate, and it helps actually clarify what we're talking about. So if I start off with the most substituted alkane and I look at the enthalpy of reaction, I release 26.9 kilojoules per mole. If I have a more substituted alkane, I release 28.5, so my starting material must have been higher because my products is always at the same level. And then finally, the least substituted, my reactants had to have started even higher because they release more energy. So what that's telling us, if I look at the relative stabilities of these starting reactants, my most substituted alkene is more stable than my least substituted alkane. Okay. So let's look at why that could be. One model that is used is that for my least substituted alkene, I literally have out here sp3 hydrogens, and they're close together. And so they tend to bump into each other because there's only 109.5 degrees between them. So that cost us energy. Where the most substituted, my methyl groups now are 120 degrees apart from each other. They're wider separation. They're going to be more stable because they're further apart from each other. So if we were to look at stability, the most substituted alkenes are most stable. And as I move to the right here to the least substituted, those are the least stable. I could also look at the substitution pattern in stereochemistry of alkenes. If I have my methyl groups in the transfiguration, those are actually going to be the most stable, again, because my methyl groups are far apart. If they are in the cis configuration, they're closer together, they're less stable. And finally, if I have them on the same carbon, these are going to be geminal groups now. Those are my least stable, but that's similar to this. Let's look at the experimental data now for hydrogenation of trans-2-butene versus cis-2-butene. When I do the catalytic hydrogenation, I get the same product. And what I find out is that I get more energy released for the cis, which means my reactants had to be higher in energy. So the heat of hydrogenation for the trans-2-butene is 27.6, and the heat of hydration for the cis-2-butene is 28.6. This cartoon drawings down here sort of show how the overlap is and why you would believe that the cis is less stable than the trans, because my methyl groups, their electron clouds are further apart from each other. Let's sort of draw all those molecules together now and put it in an energy diagram here, where I'm looking at energy, less stable being at the top here, more stable being at the bottom. They have a lower Gibbs free energy. So ethylene here, just ethene itself, is the least stable. And relative to that, if I add one R group, one alkyl group to the ethene, I lower the energy by 2.7 kcals per mole, or 11 kilojoules per mole, more stable. If I have 2 in the cis configuration, I'm now 18 kilojoules more stable. If I have geminal, that's 20 kilojoules per mole, or trans, 22 kilojoules per mole. Tri-substituted is 25 kilojoules per mole, and tetra-substituted alkenes are the most stable. Literally 26 kilojoules per mole more stable than an unsubstituted ethene molecule. So let's rank the following in order of increased stability. We're going to be looking at the substitution patterns. So let's start off and look at the first one here. This one here is tetra-substituted. I have 1, 2, 3, 4 alkyl groups on that cross that double bond, so it's the most substituted. This one down here actually has 3 substitutions, so it's the second most stable. This one has 2, 1, 2, so it's the third most stable, and the least stable is the one that's only mono substituted. And that's the end of our chapter. We're now going to go on to chapter 6 and look at alkene reactions.